concept of Newton's second law. What is Newton's second law? Force equals to mass multiplied by its acceleration. So when we have this formula, acceleration over here means this object is moving along a straight line, and you are not going to change its direction. When you change the direction, it means that there is a second force that changes direction along the perpendicular direction. But that is something we're going to discuss in this class. But other than the linear movement, a lot of time we're talking about rotational movement. So when it's rotational movement, instead of using F equals to ma, we're actually using torque equals to I alpha. This is torque. This is moments of inertia. This is angular acceleration. Okay, so when we have torque, it's actually moment. It can be foot-pound. It can be Newton, meter, or it can be any other things multiplied force together with the distance. Then that's a unit of torque or moment. And when we are talking about the angular acceleration, it's going to be radians over second squared. We're not going to use degree or any other unit for angular movement. It's always radians. So keep in mind this, when you see an angle like degree or something, you always need to convert that into radians. And other than that, those two are actually equivalent. The only difference is that the force we're talking about in the past is making everything move linearly. And when we are talking about the torque, it's moving around a specific center. So the distance between the center and your object does matter. And that is something we need to talk about, what we need to calculate for the moment of inertia in this chapter. And that idea is essentially like this. If you have S's, then your object is rotating around this S's. How are we going to calculate for the moment of inertia around this thing? Because the basic information we can obtain is its mass. Other than the mass, we don't really get any other information. So we need to know the distance over here. Meanwhile, we need to know the mass over here, and because mass is highly dependent, the moment of inertia is highly dependent on the distance between the S's and the object. So that is something we need to know. But in this chapter, we're not going to talk about single S's. We're going to talk about three S's. So most likely, you're going to encounter something like this. This is my x direction. This is my y direction. This is my z direction based on your notes and your textbook. Let's say this is area. We're talking about area. Inertia. Okay. So when I say this one is around S-axis, I'm talking about the moment of inertia around x-axis. That is something indicating this object is moving around this axis. If we're talking about it's around y-axis, it's going to be something like this. We need to know the x over here, and we also need to know something like this. Okay? So when you try to calculate the moment of inertia around x-axis and y-axis, we follow two definitions. Ix equals to the distance between the object and the x-axis. In this case, it's going to be y. And take the square of it, multiplied by the area, because we're talking about area moment of inertia. If it's going to be y, it's going to be x squared a. So it's going to be important you know its original property, which is area in this case, and we also need to know the distance between this object and the axis. You want to rotate it around, so you're going to have y squared a and x squared a. Let me ask you a question: is this possible for you to get a negative moment of inertia? It's not possible because your area is always positive, and you multiply that by the distance squared, which is always positive as well. So if you multiply those two properties together, your moment of inertias are always positive. Okay? Does that make sense to everybody? Okay. Yeah. Let's move to a more advanced topic over here. So let's say I have something like this, and this area is actually defined by an equation. So when you are dealing with something like this, you still need to come up with the answer of moment of inertia around x-axis and y-axis. So what you're going to do is you divide everything into small pieces, just like what we did in chapter 9, and doing the distance like this. However, you might notice that the distance over here is only related to the small pieces of area in the bigger shape. So when we are doing that, and I try to find everything, I'm trying to find something like this. I integrate everything based on the area. Same for y. Okay, so those are the two basic formulas you need to deal with when you try to find out the moment of inertia in terms of area. Similar to what we're talking about in chapter 9, if this object is actually not a continuous object, it can be divided into different pieces. Like this one is a combination of this piece, this piece, this piece. What you can do is using discrete type of formula, and they are actually equivalent. Using this, and you can find dA is actually equals to delta A. Y squared is actually the same. The only difference is that we integrate on your left hand side and do the summation on your right hand side. So, but everything will be similar. So far, any question? Okay. One other thing you guys need to know is when I'm using those two formulas, where are they rotated about? It's based on this formula, I mean the upper one, where is rotated about? X-axis, so it's moving something like this. How about y? It's going to be something like this, right? Okay. First thing, when we are talking about direction, what is your positive direction? We divide this in chapter 4. Clockwise. So I said this one is going to be like this, so this is my positive, so this is my positive direction. When it's y, this is my positive directions. Okay, that is something you guys need to remember. And the second thing is, when we are talking about rotation, this is rotated about x-axis, this is rotated about y-axis, but in most of the cases, we don't really care. What we care is, I'm the reference point. I need to know the moment of inertia of this object rotated around me. Most likely, I'm standing at the origin. Do you care what's going on here or what's going on here? Probably not. But you do care something like this, right? So how do we calculate for this kind of thing? It will be the same because we are talking about the distance between. Go back to the definition over here. It's the distance multiplied by the basic property. Okay, so I do need to know the distance between this object and myself. Let's name this one R. So the formula becomes what? Normally I would call it J this time. It's going to be does that make sense to everybody? So I'm standing here, I need to know the moment of inertia rotating around me. So nothing fancy, I just multiply the dA together with the distance over here. So I get the moment of inertia. But sometimes you're not given the required information like this. Sometimes you might given the moment of inertia in x and y. So how are you going to use those two? Based on the triangular relationship, what do we have? X r squared equals to y x squared plus y squared. Is this look familiar to everybody? So over here, it becomes something like this. Or if you separate everything into two terms, do those two terms look familiar to you guys? They are actually this one and this one. So we can conclude J actually equals to Ix plus Iy. So it means that you are given two moments of inertia about x-axis and y-axis. Now I'm asking you, what is your moment of inertia related to its origin? You don't need to do any complex calculation. You just add those two things together, you get your answer. Sometimes it might be easier to get this one and this one together instead of getting this integration, because a lot of times this is going to be a little bit tedious. Okay, so getting this one and this one can be easier than doing the calculation for this one. Then you essentially just add those two terms together, you get your answer. Does that make sense to everybody? Is that straightforward? Everybody understand what I'm talking about? Okay. So I want to know the moment of inertia with respect to its base. Its base is along the x direction. So we are given a triangle. We need to find Ix because I'm talking about everything related to the moment of inertia related to its base, which is this one. So I'm actually finding now Ix. But in this case, we are dealing with a continuous object, so we need to use integration method to come up with the answer. So how are we going to find the formula that we can use for the integration? That's the first thing we need to know before we start to do the integration. But which direction we're talking about over here? Based on the definition, it is y squared dA, right? So we need the distance from the bottom to here, which means if I cut this into small pieces, and we know this is y, the height over here is dy. If we can find the length over here, then we should be able to use d L multiplied by dy and get its area. And since the y is something we can know, so it's just something we can obtain. So how can we find L? It's actually a relationship because we know this one is y. So L over B. L over B is actually h minus y over h. That's a triangular relationship. This is just geometry method. Nothing fancy. The ratio between this one and this one is this one with this one. So we know this is h. This portion must be h minus y over here. So we can use this relationship based on the configuration I draw over here on the triangle. Does that make sense to everybody? So what we need to find out L in terms of y. So L is actually B over h minus y. B and h are the constant even in the beginning. No, forget about it. Forget it. Okay. So we need to assemble this